So in this video we'll look at the families of compounds, well, one family of compounds in particular, alkanes. But just in organic chemistry it is necessary to group similar compounds, if you like, based on their structure. Indeed, that and their chemical properties then is obviously linked to their structure and the atoms in them. So essentially the name for that is homologous series. So remember when we said homogeneous catalyst means the homo part means the same. So in homologous series, effectively we have a series of compounds that have similarities. And normally that means that they adhere to the same general formula. So we'll worry about that in a second. We're just going to look at alkanes today. It's a very simple way of naming compounds compared to perhaps the same type of principle is used in biology, where different molecules or different families of animals are grouped together. Like, you know, you have arthropods or crustaceans, so they're families, if you like. Well, in organic chemistry it's the same thing, and there's a lot less in organic chemistry than there is in the living world, if you like. So what we're going to look at is hydrocarbons. We're going to look at initially. And this is most of your course, to be honest, and we look at some variations of it, but this is effectively all of your course. And the main thing that we look at today is alkanes. So that's these. Now, aliphatic hydrocarbons are essentially hydrocarbons that don't have delocalized electrons like aromatic. Now, for leaving cert, you basically say that aliphatic hydrocarbons are not aromatic. Now, aromatic I'll go into with you in a later video, because there's something to talk about there. You see these double and single bonds around this ring here. This is known as a benzene ring. It turns out that that's just a representation of it. If you look carefully, what actually is the case is that the benzene ring is this double bond, and this double bond. The double bonds are actually spread out among them all. Those 6 electrons, you know, the 2 that were there, the 2 that were there, and the 2 that were there. Just the second bond, I mean, the double bond, if you like, the one that makes up the second one. So they're spread out around those carbons, and what is known as delocalized. You know, if flooding is localized in an area, then it's very specific to one area. If it's delocalized, it's spread out. And it's the same thing here for electrons. They're not localized between 2 carbons, these double bonds. They're spread out among all 6. And it's a very, sort of unusual thing. It was relatively late discovery. Initially it was thought that there were individual double bonds. But what they found out was the bond length between the carbons was actually halfway between a double and a single. And it was the same all the way around, and that kind of led then on to the principle of delocalized electrons. But we're going to focus heavily on alkanes, so that's what we're going to talk mostly about, well, all about in this video really. Aliphatic, so these alkanes, cycloalkanes. The cycloalkanes, see this, if you look carefully, there's a difference between this structure here and this one. So there's no double bonds between the carbons. So there's no delocalized electrons there. They're all localized singled bonds, you know, localized in one place. And that's what's known as a cyclic. Cyclic, quite much like a bicycle. A bicycle has round wheels, and the bi stands for 2 wheels. Here the cyclic is the round nature of that structure, as opposed to it being linear, something like this. Alkanes, don't worry about these. We're going to go through these in detail. Not in a huge amount of detail either, actually, but this is all the basis of sort of families of compounds in organic chemistry, so it leads on from that. So like I said, we're going to focus heavily on this group, the alkanes, today, and then we'll look later at the alkenes and the alkynes, and that's effectively the main ones that we'll look at. In terms of aliphatic. Aromatic hydrocarbons, we don't really go into that much in leaving cert. We study a little bit about benzene, and I'll show you some ones like methyl benzene. Toluene is a lot of time used in a lab. You know, just to give you a note, like every time you see this juncture, there's a hydrogen off it, you say. There's no second hydrogen, obviously, because you can think about there's 1 bond, 2 bonds, 3 bonds, 4 bonds. So there's only 1 hydrogen off every one of these corners. And in organic chemistry, when you make a corner like that, then it's assumed that there is a carbon atom there. And it's also assumed that it's saturated. What that means is that it has its maximum 4 bonds, something we talked about in the last video. So just to be clear on that, so there's 1, 2, 3, 2 involved in that double bond, even though it's delocalized, but anyway, 1 that way, so there's 1 more off to a hydrogen. So there's a hydrogen off every one of those carbons, essentially, all the way around. Wouldn't worry too much about this for now, but just so you have some idea before we go into it later. So the homologous series adhere to some similar general formula, and they have similar chemical properties because they have what's known as the same functional group. Now this is an important word. The functional group of a family of organic compounds is essentially the part of the molecule that determines its chemistry, is dominant in determining the chemistry. So effectively what I mean there is it's the thing that makes it distinct from other families. So, you know, if you were to talk about animals, it might be the ears of an animal are quite distinctive. Something that is functional, something that is very different, or the coat that the animal wears. Well, this is just one part of the molecule that's quite different to the rest. These are some examples. Like, we're going to look at alkanes today, and what makes alkanes distinctive, if you like, is again, every time you see a corner there, you may assume there's a carbon. So there's carbons at each of those points, and indeed at the end there's a carbon there and a carbon there. So those lines represent 2 electrons as well. So anytime you see that in organic chemistry, it means there's a carbon there and a carbon there, and they're sharing a pair of electrons. That's what that means there. But anyway, you don't go into too much. Normally in leave insert we draw this type of thing, a much more obvious structure, but just because it's there. Alkenes, what makes them different is this double bond. They have double bonds in them. An amine, we don't look at this leave insert, but this is just to show you. It has a nitrogen bonded to 2 hydrogen. Alcohols, we do look at it in leave insert chemistry. It has there's a carbon here, and then there's some chain after it, some shape of a chain. So this would be the simplest one I'm drawing now. If I had a carbon, then instead of that R and then 3 hydrogens, that would be known as methanol. Methanol because it ends in OL, you see. Meth because there's 1 carbon. We'll go through that anyway. We don't look at the ethers at all, leave insert. We do look at carboxylic acids. What makes them different, again, there'll either be a hydrogen or a carbon here. In this case, it would be a hydrogen. Or in this case, I'll draw in a carbon, I should say. You could have just a hydrogen there, though. And that would give you that structure. Or actually, you wouldn't just have a hydrogen. That would be the minimum there. So that would give rise to what is known as... if you look at the number of carbons here, it's 1, so it's methanoic acid. So methanoic acid is actually what's in bee stings, or not bee stings, bee stings. And that's effectively, or indeed in ant stings or in nettles, methanoic acid. We don't look at amides either. We do look at esters. Essentially, if you look at esters and carboxylic acids, they're very similar. This part is the same in both of them, if you notice that. The only difference is instead of having a hydrogen here, you have a carbon and some extension. But in any case, again, this is just an introduction of functional groups, just to show you that each molecule has its own distinctive little part. So much simpler today. What we're going to look at now is alkanes. And that's the first member of the family. Now they're denoted with this ending ANE. So that's why organic chemistry is very simple after a while to talk about it, because if you like, its name gives away a lot of its structure. And they consist of, I think I mentioned this already, it's always single covalent bonds in an alkane. And those single bonds are either to hydrogens or they're carbons. You see, this is the simplest member right here. Where methane, that's a carbon bonded to 4 hydrogens, the simplest member. Ethane, a carbon, you see the eth, that stands for 2 carbons. And that's not just for alkanes, that's forever and forever. Meth is 1 carbon. Eth is 2 carbons. Prop is 3 carbons. Bute, 4 carbons. Pent, 5 carbons. So I think, in some languages, the penta or a pentagon or that has 5 sides, obviously. Hex, 6 carbons. Hept, 7. Oct as well is sort of a prefix that's used in languages, right, to denote 8 carbons. Non is 9, and dec, we think about a decade. Dec is 10 carbons. Now, to be honest, guys, in Leavens chemistry, we sort of hover around the first 5 mostly. So somewhat the 6th and 7th for alkanes, but not for other families. And it's rarely we go up to something like 8 or that. We might mention it, but they're said to be saturated carbons. The reason that they're saturated is, if you look at every hydrogen, if you just pick, let's say, propane here, remember it's prop because it's 3 carbons, and ANE because it's an alkane. But if you look at it, like every carbon from the last video we talked about what makes it so special, every carbon has 4 electrons to involve in covalent bonding. 1, 2, 3, 4. There is no more valence electrons there to create another bond. Therefore, and if you look at all of them, they're that way. It does have 4 bonds, but they're to 4 different atoms. There's no way of breaking or adding, I should say, another atom on there, another hydrogen. And that's the same for all of these. You can't add anything on. What you could do is break away a hydrogen and add something, but you'd still end up having 4 single bonds around this carbon. So you basically can't add anything without taking something away. And that's considered to be saturated. So it's a bit like a sponge. A sponge is saturated when it cannot hold any more water. So therefore it is considered to be saturated at that point. These molecules are all saturated. They cannot hold any more atoms, whether that be another hydrogen or any other atom. Now it is true you could take something away and add something, but that's not, that's besides the point. That's not the same as adding something without taking something away. So that's all saturated means. And think about a sponge. A sponge is saturated, or a piece of cloth is saturated when it cannot take on any more water. The alkanes have a group of hydrocarbons which conform to the general formula CnH2n plus 2. Now this looks a lot more complicated than what it is. Basically the C is the carbon. So there's 1 carbon. And H, to get the number of hydrogens, look at N is N. So multiply the number of carbons by 2. So 2 times 1, if we were to look at this methane molecule. 2 times 1 plus 2, 4. 1, 2, 3, 4. So there's CH4. Like there's no real, it's rare, like they're not, they may ask you what's the formula, general formula for it, but I mean you could draw it out and figure it out. Put 1 bond in every hydrogen, make sure there's 4 bonds around the carbons, and they are 4 bonds to 4 different atoms. You know what I mean later why I keep saying different atoms? Because there's no double bonds is what I'm saying. But look at here, like CN, C2, and then that's right, so you know that the number 2 there, so it's C2, and then how many hydrogens? Go back up to the formula here, 2n plus 2, so 2 times 2 is 4 plus 2, and that will give you a total of 6. And then you see what I mean, you could have drawn it out as well, so it's not the end of the world. Look at 1, 2, every carbon is 4 bonds, 1 to another carbon, and then that'll give you 3 hydrogens, and so C2H6. But it can also be written as CH3, which is a bit more expanded if you like. And what that means is that it's a bit more evident that there's 3 hydrogens on the first carbon and 3 hydrogens on the second carbon. But both of these are fair ways of describing the ethane, or writing the chemical formula for ethane. Now the chemical formula is written like this. That's what we always write. When you write H2O, that's my apologies, the molecular formula I should say. So that's its molecular formula. How many hydrogens, how many oxygens. Here, how many carbons and how many hydrogens. Just be careful, this is what's known as its structural formula. The structural formula is drawing it out like this, if you like this right here. Whereas the molecular formula is giving the number of atoms. Now, I think we've mentioned that before, but I'm just afraid that you would use the word chemical formula. Chemical formula is too general. Both of those are chemical formulas. Therefore, you can't say that this is the chemical formula because, you know, it could be either of those. So just be clear. If you like, the chemical formula is more general, and then within that you have the structural formula S, and then you also have the molecular formula M, let's say. So there's the molecular formula, there's the structural formula. Now this might seem heavy going, but it's like playing with Lego. I mean, there's very little, essentially, once you get used to this, it's very, very repetitive. I mean, every carbon, if this was a carbon atom, every carbon has 4 bonds to it. So like we were to make the first member there and there was 4 hydrogens around it. There's 1, 2, 3 and 4. So that's the methane molecule. Never forget, guys, and it's very easy to forget, that when we draw these formulas like this one right here, the people get into the habit of thinking it as a 2D thing. It is not, it is 3D. And remember when we looked at the shapes in the last video, and indeed earlier in the year, that this is tetrahedral. Those 4 bonds around to 4 different atoms around this central carbon will try and be as far away from each other as possible, for the simple reason that electrons repel each other and bonds are made out of electrons. So please remember that. And that brings us to the alkanes. Building the members then, I think this might be relatively straightforward for you, hopefully. I mean, a carbon has 4 valence electrons. Okay, it has 2 inner electrons. I mean, they're not involved in bonding, so we're not going to bother drawing them. And then each hydrogen has 1 valence electron. You see them here. And then if you have the carbon and you create covalent bonds, look at, you get 4, 1, 2, 3, 4. And there's the, if you like, the shared pair of electrons in each case. Carbon has no other electrons off its off the central carbon atom, and therefore you get that tetrahedral. And don't forget, it's 3D. It's so easy when you draw this over and over again. Indeed, many people do. They forget the principle. The IUPAC, International Union of Physical and Applied Chemistry, is a system. You should know those prefixes, but you know, you can look that up. It's in the notes in any case that I'll send you. But yeah, it depends on the homologous series. So the suffix, we're going to have a look at it in any case. Meth, like I said, is 1 carbon, sorry. Eth 2, prop 3 carbons, and this will last you all the way through chemistry. If you pick up a can of deodorant and you see bute on it, that indicates the principle that there is 4 carbons involved there in some way. Pent is 5, hex is 6, hept is 7, oct is 8, and non is 9, and dec is 10. So for alkanes are end in ANE, so I've said that to you already, and you know, you could write those out a few times and play around with them to get used to this. Like, it is sort of a thing you need to get used to, and you know, there's very little I'd ask you to learn off in chemistry, but this is one of the things we sort of, these prefixes here. I mean, we'll have to know that meth is 1, eth is 2, prop is 3, bute is 4, pent is 5, hex, hept, oct, and I would learn up to 10. This is ethane, the same sort of thing again. Like, every carbon has 4 valence electrons, there's 2 of them. If we look at the total number of 2, 4, 6, 8, or there's too many hydrogens there, 2, 4, there should only be 6 there really, but in any case, and then you create single bonds between those, and there's a single bond between the 2 carbons, and you see every carbon ends up with its stable 4 bonds around the central atom, and that gives rise to this molecule. Again, just to re-emphasize the fact, never forget, and it's so easily done, that these are 3D. So if I put the shapes together for that one, you should always, you should think about these shapes in your head when you're writing them, rather than writing them just like you would write English or a novel. Like, think about what the shape is. So there's the shape, there's the 3D. Both of those are tetrahedral, remember. I mean, if you just took this carbon, it has 1, 2, 3, 4. And then if you take that carbon away, this carbon, 1, 2, 3, 4. Just because that bond is to another carbon doesn't take away from the fact that this carbon is around this atom. So it's 1, 2, 3, 4. And likewise here, 1, 2, 3, 4. All the way around, 1, 2, 3, 4. So you should always think about that when you're drawing them, that they are 3D. Propane, you see it starts building up then. There you have propane. So now we have the correct number of hydrogens here. And that again is 3D. And they're all single bonds again. Now obviously this is drawn out very much. I mean, you can go straight to them after a while. I mean, you figured out butane is 4 carbons. Join up the 4 carbons, 1, 2, 3, 4 single bonds. The line represents a single bond. And then create or saturate it then with hydrogens. And you see what I mean? I mean, you could work out the general formula just from knowing that every carbon will have 4 bonds, and in this case, because it's an alkane, 4 single bonds, and every hydrogen will have 1 bond. I mean, it's like playing with Lego. You can just add those together. And there's pentane. You see, that brings us up to that. Hexane, 1, 2, 3, 4, 5, 6. Heptane, 1, 2, 3, 4, 5, 6, 7, 8. You see, that's an error there. That should be octane. That has 8 carbons in it, octane. So that shouldn't be heptane there. Oh, there is octane. 1, 2, 3, 4, 5, 6, 7, 8. Nonane and decane, just to elaborate on it. The first member of the group, so we've gone through that. You see, each time, if you look at patterns, what's being added is CH2. CH2. That's what's gained every time you go up a member in the alkanes, which is sort of interesting. Don't forget that they are 3D. And remember, like, this notation is not important for Leavens, but if you ask me, it is important, because like if we drew this the odd time, it always remind us that it is tetrahedral. Because the molecule, you see, it is possible for this to rotate. It can rotate, so that's what that diagram shows. The fact is, that's just a single bond, so they will arrange themselves like all the atoms on their surface have electrons, remember, so they'll always rotate in such a way that the electrons are as far away from each other as possible. It's all about repulsion around central atoms there, and atoms across from each other. So you see, you end up with this sort of a shape, and we've talked most about that. Now the other little thing we must look at here is that it is possible to have different shapes of the same molecule. Actually, you know what, perhaps we have enough done at this point. What I'll do is we'll go on to isomers and a separate one, but maybe if you want to think about this, I mean, there's 1, 2, 3, 4 carbons there in a row. It would be possible for that hydrogen to come down here and come off that, and for this whole piece here to create a single bond here. So what I mean, it might be easier if I show it to you here briefly, and then you see that's the same number. If you counted all the carbons there, 1, 2, 3, 4. If you count the number of hydrogens, there's 10. So you see, it's the same thing as, or the same number, so it would have exactly the same exactly the same molecular formula, but it has a different structural formula. But in any case, let us leave that and we'll look at that in a different video.